So again, the planes are going to be one of those few surfaces that we will plot by hand. So I will show you the trick. Okay, number one. So before we go and graph a plane, let's review how do we graph a line. For instance, the line 3x plus 12y equals to 24. All right. So let's say we want to graph that line. Let's review the different ways to graph this line. Okay. Any ideas? How do we graph this line?
We pass the 3x to the other side and
Yes.
divide by 12.
Okay, and then
So rise over run.
together to do the rise over run, right? So that's one way. So we would go about whatever the y-intercept is, and then either go upstairs or downstairs in accordance with the value of the slope. Any other ideas? Any other ways to graph this line? So yeah, that's one way. Another way. Yes.
You just plug in coordinates and then you just get an answer out.
Mm-hmm.
Just put them all down.
That's another way. Is there another way? There's another one. Yes. At least one more. So solving for y and then use the rise over run approach. That's one. There's another, plotting points, making the typical table of values, right, to get order pairs. There's another one. And it's even quicker, by the way. That's actually the one we're going to use to turn it into 3D and then sketch the plane. Add a C. How do we add the C? Okay. Is there another one? Yeah, there is another one. You give up? Yes. How about finding the intercepts? Right? The x and the y intercept. How do we find the intercept, first of all? Set one variable equal to 0, right? So we get the x-intercept by setting which variable equals 0? Y. We find the y-intercept by setting the other variable equals to 0. So that's also known as the peekaboo method. Did you know that method like that? The peekaboo method? No? Well, so essentially, peekaboo the x and solve this equation, divide both sides by 12 to get y equals to 24 over 12, that equals 2. Now let's peekaboo the equation or the peekaboo the y variable. So that's going to give us 24 over 3, that's y equals to 8. All right? So the line will look like this. 2 units, 8 units, and connect the dots right here, right? So that's another way, quicker way to sketch lines, right? Rather than making a table of values, which is fine if you feel more comfortable doing the values, or using the rise over run approach. So we're going to use this. We're going to take this approach to graph planes, okay? So but peekaboo, we have 2 eyes only to peekaboo, right? But in this case, for planes, we need 3 eyes. How are we going to peekaboo 3 eyes? Have a little guess for that. About this guy, right? Okay, let me put a picture of it for the people watching on the video. I have this alien right here. Well, so how are we going to peekaboo? Well, so each eye will represent the variable x, y, and z. And well, to find the intercept with 3 variables, we're going to peekaboo 2 variables at a time. So if I want the x-intercept, I'll peekaboo y, and z. If I want the y-intercept, I'll peekaboo x and z. If I want the z-intercept, I'll peekaboo x and y. All right? So that's the approach we're going to take here. So that's what we're going to do to graph this plane. Okay? So sketch the plane to x plus 4y plus z equals to a. So, and express the intercepts as points, not just values. Notice in the preliminary example, I just came up with values. Of course, those are the y value and the x value where they intersect. But in the end, when we are asked for intercept, we're supposed to express those as order pairs. I mean, rather, order triples in space. Okay, so let's go about it. So what about the x-intercept? For the x-intercept, let y and equal to z equal to 0. That means peekaboo y and z. That's going to leave us with the equation 2x equals to 8, where x equals to 4. So that means the order triple will be 4, 0, 0. Right? The y-intercept. The y-intercept, that is peekaboo x and z. That's going to leave us with the equation 4y equals to 8. That means x equals to z equals to 0. That is 4y equals to 8. That means y equals to 2. But again, the order triple that describes the intercept is going to be, careful, we made x and z equals to 0, 0, 2, 0. Right? And lastly, the z-intercept. The z-intercept will be by setting x and y equal to 0. That is peekaboo x and y. That's going to be, so x equals to y equals to 0. That is simply z equals to 8, which will describe the order triple 0, 0, 8. All right? And we have the information we need to graph the plane. Okay, so let's draw a 3D space. So that is, okay, I'm going to go, okay, this is x, y, and z. Okay, so that'll be 4 units in the x direction, 2 units in the y direction, and 1, 2, 3, 4, 5, 6, 7, 8 units in the z direction. So we're going to trace what we call the traces, right? By the way, in this case, we're not graphing the entire plane. We're just graphing the portion of the plane that displays in the first octant. Notice the word octant. In this case, since we are in space, there's 8 octants in a similar way that there's 4 quadrants in the 2D plane. All right, so 8 octants. So the first octant, it's the octant that contains the 3 variables with positive values. And then you go around the second octant in a similar way that you go with the quadrant. And then you go below to describe, below the xy plane that is for z is negative, to the remaining 4 octants. So that's how we graph this plane. Looks a whole lot like a tetrahedron, right? Well, actually, when we get to the double and triple integrals to find volumes, masses, and a bunch of pretty cool stuff, we will have these solid regions under these tetrahedrons. Well, that's going to be later, but at least you already have that tool to graph those solids. Okay, so they're also asking us to describe and graph the traces. Well, what are the traces? Well, so there's 3 traces. Let me label them first. Because this diagonal line involves the x-axis and the z-axis, this is the x-z trace. Because this diagonal line right here involves the x and the y variable, this is the xy trace. And because this diagonal line right here involves the y and the z variable, this is the y z trace. Notice those diagonal lines also only involve two variables. We should eliminate one of the variables. Well, how do we do that? Well, for instance, if I want to describe the xy trace, so the xy trace right here, well, which letter is missing from the 3? Isn't that the letter z? So that means we need to make or set z equals to 0. All right? On another peekaboo, but in this case, it's just one variable we will peekaboo this time. So for traces, we peekaboo one variable. For intercepts, we peekaboo two variables. Okay? So that means z equals to 0. That leaves us with 2x plus 4y equals to 8. I know they're all multiples of 2, but for now, leave them like this. That's fine. Okay? All right, what about the y z trace? Notice in our label here, the x variable is the one that is missing. That means we need to set x equals to 0. That's going to be this trace right here. So make x equal to 0, cross it out. That's going to leave us with 4y plus z equals to 8. And lastly, for what's the other one? xz. The xz trace. Notice in the label, it's the y variable that's missing. That means we need to set y equals to 0. And it's going to give us this diagonal line. Cross out the y. Make it y equals to 0. Essentially, that's going to leave us with 2x plus z equals to 8. All right? So these three equations right here, these equations describe these three traces that we use to form, well, later on we're going to call it the armor of the solid, but for now these are our guides to draw the surface in the portion of the surface in the first octant right here, right? So right now it's just a surface, it's just a plane, not a solid yet. That's a layer, okay? So that's our example of how we graph a plane. Okay, so now let's do more algebra with planes, lines, points, angles. We're going to do a bunch of pretty cool stuff here. Okay, so let's have a look at the next topic, the next example, finding the intersections of lines and planes. Okay. Let's find the intersection, if it exists, of the line given by the vector valued function and the plane of 2x minus 5y plus 3c equals to 45. So how are we going to do this? Because, okay, we have a vector function, and we have a scalar function. So how are we going to put those two together if they are both of a different nature, so to speak? So it turns out that somehow we can do a very simple substitution here. So, okay, let me highlight. No, that's not the highlight. So I'm going to highlight the x component of the vector valued function. What we're going to do here is we're going to substitute the x component of the vector valued function in the x variable in the equation of the plane. Then we will substitute the y component of the vector valued function into the y variable in the equation of the plane. And last but not least, the z component of the vector valued function is going to go in the z variable of the equation of the plane. All right? Very simple substitution. That's going to lead to a very nice and simple linear equation. You'll see. Okay, so that means 2 times x, but what's x? 3 plus 2t minus 5 times y, but what's y? That's a negative t. And lastly, plus 3z, which in this case, that's 5 plus t. And that equals to 45. Okay? If you want to keep highlighting, well, let me highlight, and highlight. All right? so let's solve this baby linear equation. So that is 2 times 3, that equals to 6, plus 2 times 2 equals to 4t minus, minus, that becomes a positive 5t. 3 times 5 equals to 15, plus 3t equals to 45. Okay, so combine the t's together, combine the constants together. That's going to leave us with 12t plus 21 equals to 45. Solving for t, that's 12t equals to 24, and t equals to 2. But hey, that's not the point of intersection. That's not the point of intersection because, okay, so again, get my plane and my so this is a line. This is the given line in space, the r of t, which eventually intersects with the plane, all right? However, keep in mind that along this line, there's a particle moving along, right? There's a particle moving along this line. So we have different positions, different points at different values of t, at different times, to keep it simple. So we are looking for the specific time at which the line will cross with the plane. What is that value of t? Well, what we just found. After 2 seconds, if you will, okay, or 2 minutes, or 2 hours, depending on the context. We don't have any context in it. Oops. So that means we need to go back to the beginning, the vector valued function, and evaluate that at 2. That is 3 plus 2 times 2, negative 2, 5 plus 2. And then just simplify all this. 4 plus 3 equals to 7, negative 2, 7. But again, this is not a point. This is a vector. We need to express it properly. We're looking for the intersection point, not the intersection vector. Well, in the first place, that doesn't make sense. Intersection vector, right? So no. So that means the intersection point, it's 7, negative 2, 7. Again, why can't we simply go from vector notation to order triple notation? Because, again, those points that are on the line are the terminal points of all these vectors or in standard position that come from the origin to whatever point on the line. So that's why we can interchange this notation. All right? Okay. Let's keep talking about planes. Planes in the 3D space can be parallel or may intersect in a line. Well, I'm talking about the case with 2 planes only. All right, if they intersect, then we will be able to find the angle in between the 2 planes, and also find the equation of the line where they intersect. Well, so here's my plane. 2 cases. Number 1, the 2 planes are parallel. They will never cross, right? So that means most likely they have the same direction vector. They will have the same coefficients of x, y, and z with a different right-hand side value, right? Or a multiple of that vector. That doesn't matter. That's the one case. But then we have another case, the case where they intersect, like this, right? So we have 2 intersecting planes, right here. So if we see the planes in this perspective, notice there's an angle right here. Oh, but there's also another angle there, all right? So we will find the angle in between these 2 planes. But the rule, okay, let's have a look at point A right here on the notes. The rule, the angle we would be finding would be that that is in between 0 and 90 degrees. So it's essentially this angle, right? The acute angle, not the obtuse angle. But the question is, how do we find that angle? All right. So let's find the angle between 2 planes. 2x plus 3y minus z equals to negative 5. X minus 2y plus 4z equals to 1. Actually, this is a 2-part question. So number 1, so let's say this plane has a direction vector. Let me call it n1. and because it's a normal it's a vector that is normal to the plane, and 1 because it's the first plane. We have 2 planes. That is 2, 3, negative, negative 1. And over here, n2. That is 1, negative 2, 4. Those are the 2 vectors that we're going to find the angle of, and that's going to be equivalent to finding the angle in between the planes. Okay, so to find the angle between 2 vectors, so theta equals arc cosine of, well, in the earlier formulation for section 3. Whatever that was, we did u dotted with v divided by the product of the magnitude. But in this case, we don't have u and v. We have n1 dotted with n2 divided by the magnitude of n1 and the magnitude of n2. All right? So, number 1, let's find the dot product. n1 dotted with n2. That is 2, 3, negative 1, dotted with 1, negative 2, 4. Okay? So, 2 times 1, that is 2. 3 times negative 2, negative 6. Negative 1 times 4, minus 4. That equals negative 8. Okay? That is negative 8. So, magnitudes. The magnitude of n1, which is, what's that? The square root of 2 squared plus 3 squared plus negative 1 squared. That means that equals to the square root of 14. And for the magnitude of n2, that's the square root of 1 squared plus negative 2 squared plus 4 squared. That equals the square root of 21. All right. So we have all the information we need. Let's just substitute it in the formula for the angle for the angle between the 2 vectors. Okay, so theta equals to arc cosine of the dot product, which is, what's that? Negative 8, over the product between the 2 radicals, square root of 14, square root of 21. Okay, so using our calculator, there's going to be a little catch here. Check this out. So we're going to get 117.8 degrees. All right? That's not the correct answer, unfortunately, because again, what's the rule for angles between 2 planes?
Between 0 and 90.
0 and 90 degrees. So actually, we're getting...
So we have to subtract for 180 degrees?
Exactly. That result is essentially the obtuse angle. We want the acute angle by subtracting 180 degrees. All right? Let me call this theta prime, so to speak. That is 180 degrees minus 117.8. That is equal to 62.19. Right? As a note, we want the acute angle. So we want the acute angle right here, right? All right. So that's part A of the problem only. What's part B about? So for part B, they are asking us to find the parametric equation or as a vector valued function, actually, either way. Well, I'm going to write it in vector form, all right? The parametric equations of the line of intersection between the 2 planes. Okay, so now that we have two intersecting planes. This is the picture right here. Do you see these 2 planes intersecting on a line? Right? So we're going to find the equation of this line of intersection between the 2 planes. Oh, this is going to be a pretty interesting algebraic process. So, okay. How are we going to do this? Well, so we're given two planes. That is 2x plus 3y minus z equals to negative 5. So, and the other plane, what is it? X minus 2y plus 4z equals to 1. Okay, guys, so this is the first time I will solve this problem in a different way. I think it's a way shorter way than the way I used to do it when I teach it the past semesters. And I like this one better. I like this method better because the way MyLab is going to ask you to do this takes forever. It's going to ask you to solve two systems of equations with three unknowns. And it takes a good minute to go. So instead, I'm going to take the substitution approach. So yes, most likely you have never solved a system of equations with three variables using substitution. You always use the elimination method, right? But well, you'll see how is this going to work a lot better. Okay, so let's have a look at the two equations and look for the easiest variable. What do I mean? The easiest equation. That means an equation that has a 1 as one of the coefficients. And it looks like the second equation, it's our guy right here, right? So this is what we're going to do. I'm going to solve for x in the second equation. That is 1 plus 2y minus 4z. What am I going to do here? I'm going to substitute this x right here, okay? I'm going to substitute it there. That's going to give us 2 times all this madness here. 1 plus 2y minus 4z plus 3y minus z equals to negative 5. Okay? So that's going to give us a single equation. One equation with two unknowns, which is still somewhat a problem. Right? But trust me, it's going to get a lot more simple. So that'll be, okay, distributing the 2, that's 2 plus 4y minus 8z plus 3y minus z equals to negative 5. Okay, let's combine like terms as usual. So that's 4y plus 3y, that's 7y, minus 9y, minus 9z, not y. And what's that? 2, the plus 2. Plus 2 equals negative 5. So I'm going to solve for y here. You could solve for a z if you want, but I'm going to solve for y for a reason here. Okay, so that's 7y. Okay, I'm going to subtract 2 on both sides to get negative 7. And, well, actually, and 9z rather, minus 7. All right? So 9z minus 7, and solving for y, that equals 9/7 z minus 7 over 7 minus 1. I mean, how is that going to get us out of trouble? Because yes, I mean, we started with two equations with three unknowns. We sort of reduced the problem, but we still have one single equation with two unknowns. So you might remember from the theory of systems of equations, when you have this case, you have a free variable. So, and it doesn't matter what variable you choose to be your free variable. It could be the y or it could be the z. So that's why I solve for y, to make the independent variable, in this case the z, make it a t. That means let z equals to t. That means from here y equals to, what's that? 9/7 t minus 1. So we already have the parametric equations for z and y. We just need to get those for x. Go back to the beginning, the one that we highlighted, and substitute your y in terms of t and your z in terms of t. That's going to give us x in terms of t. That's 1 plus 2 times y, which is 9/7 t minus 1 minus 4z, which in this case is simply t. So that is x equals to 1 plus 18 seventh t minus 2 minus 4t, and combine like terms again. That is, x equals to 18 sevenths t minus 4t. That gives us negative 10 sevenths t. And 1 minus 2, that's negative 1. All right? So we have the three components. Now let's express it as a vector valued function. All right? Oh yeah, we are required to write it as a vector valued function. So r of t means it is, what's that? Okay. X, which is negative 10 over 7 t minus 1, comma, y, which is 9 over 7 t minus 1, and z, which is t. So here is the thing, guys. Just in case you decide to take a different approach, just in case you are at this point right here, and instead of solving for y, you decide to solve for z. That's valid. That's fine. How is that going to change? Well, you're going to get y equals to t, z equals another expression of t, and then, well, an x expression that is going to look different than the ones we have. And it turns out that it will be equivalent. If you plot it in GeoGebra, you should get the same picture, which, by the way, that's the next part. Show this in GeoGebra so you can visualize this better. Yes?
One of the parametric equations of the vector value equation.
Yeah. So typically it would be the vector value function only. Yep. But I mean, here we have the parametric for z, for y, and then for x. It's just that I didn't put them together. But yeah, we just got the vector value function. Okay, let's go to GeoGebra. Okay. So that was example number 8, right? Okay, example number 8. That's supposed to be here. Okay. So what did we have? Two planes, the two given planes. Do you see how these planes are intersecting at a line? Right? What is that line? So here I have the equations of the line that we just found algebraically. Negative 10 sevenths t minus 1, 9 sevenths t minus 1 also, and t. And I'm declaring the variable t to go between negative 4 and 5. I mean, we don't have to go between 0 and 1 or between negative 10 and 10. You can choose your favorite interval, preferably an interval that is visible in your window here. So let's have this showing here. And there it is, right? That's the intersection line. It overlaps perfectly, right? That's a very useful tool to verify everything we do by hand, and that's actually it's very satisfying because all the algebraic process we do, but in the end, what the hell are we doing anyway? What's the visual? What's on the behind the scenes? It's there, right? Okay, so let's move on through the topic, and now let's find a distance between. Oh, wait, no, there's another problem. Oh, for this problem, I like this one. This is the, yes.
Oh, quick question. Why did you put z equals 2?
You can choose your free variable to be whichever you want, whatever you want. You can set your t equals to y, but you will get a different equation for z and a different equation for x. And in the end, it doesn't matter. You will get the same visual in GeoGebra. It's just that. Okay, from calculus 2, parametric equations are not unique. There's infinitely many ways to represent a parameterization of a function. You know, for instance, if you want to parameterize y equals to x squared plus 5, all right? There's infinitely many ways to parameterize this one. For instance, and in the most common way is to give the independent variable the t. So that would look like t squared plus 5. I mean, no. This is t, and this is t squared plus 5. But that's not the only one way to express it. You can make your x to be e to the t. That will be e to the 2t plus 5. All right? You might want to do instead arctan of ln of t, right? And your y, that's arctan squared of ln of t plus 5. And that's gonna give you a very similar graph. So there could be some restriction depending on what you want. So despite the parameterizations look totally different, they will give you the exact same graph. All right, here I'm exaggerating with this, but I mean, you can modify just coefficients. That's good enough, not something as crazy as this. Okay. All right. Find the equations of the planes that have that intersection line. So in a way, we're doing the same problem we just did, but backwards. How are we going to do that? Okay. So this is x, this is y, and this is z. Agree? Okay, I'm going to set 3 equations. X equals to 1 plus 3t. Y equals to negative 2 minus 3t. And 4 plus z equals to 4 plus t. This is what we're going to do. We're going to solve for t on the 3 baby equations here. So that's 3t equals to x minus 1, and t equals to x minus 1 over 3. This is going to be negative 3t equals to y. Okay, minus 2 goes to the left-hand side. Well, to the other side with the opposite sign. That is y plus 2. All right? And then t equals to y plus 2 over negative 3. And here we just need to solve for t. That's t equals to z minus 4. All right? How are we going to get the equations of the planes anyway? I wonder why did we solve for t in the 3 baby equations here. Okay, that's because we're going to equate equation. That's kind of redundant. That's kind of weird. That's because, if t equals something, this t equals another something, t equals another something, we can set t's together. So I'm going to set t's pairwise. I'm going to put these 2 together, and I'm going to put these 2 together. All right? So from here, this means x minus 1 over 3 is equal to y plus 2 equals to negative 3. And over here, y plus 2 over negative 3 equals z minus 4. All right? And notice how in those 2 last equations, we just got rid of the variable t. And we have equations that depend on x and y. And because of the powers 1, well, that indicates that we're going to get equations of planes. All right? Okay, let's get these equations of planes in, in standard form, right? Is that standard or... Yes, it's... I always mix them up. Okay, in general form. Okay, so I'm gonna cross multiply. That's a negative 3 times x minus 1 equals to 3 times y plus 2. That's negative 3x plus 3 equals 3y plus 6. That's gonna give us, okay, let me move the variable terms to the left hand side. That's negative 3x minus 3y. And let me subtract 3 on both sides. That's going to give us a 3. So in the end, that's going to be the equation negative x minus y equals to 1. All right? So that's one equation of the plane. Well, one variable is missing, the z variable. It doesn't matter. That's fine. No problem. Okay, let's do the same with the second combination of equations. So I'm going to cross multiply. So this is technically a z minus 4 over 1. Cross multiply those 2. That's y plus 2 equals to negative 3 times z minus 4. Y plus 2 equals to negative 3 z plus 12. Okay, let me add 3z to both sides. That's y plus 3z, and subtract 2 from both sides. That is equal to 10. So those are the 2 equations of the planes having that line of intersection. All right? Actually, we could get a third plane. You know why? Or do you see why? So notice how we... Yes?
we like pair up X and Z.
There you go. So we paired the first one with the second one with the third one. We can pair the first one with the third one and get a third plane. But in this case, we are required to find only, well, actually, there's no restriction, but I'm just going to do 2. All right? 2 is fine. All right, let's show this in GeoGebra. Why not? Right? So, okay, so that's example. No, okay. I think this will be the last GeoGebra for the chapter. Okay, so that's the regular perspective. Okay, so this time we're going to start with the equation of the plane. All right? I mean, not the plane, of the line. So we need to find 2 planes. We just did algebraically, having this line of intersection. Okay, so I just type them here. Negative x minus y equals to 1, the first plane we got algebraically, and y plus 3z equals to 10, the same plane we got algebraically, right? There you go. What do you think? Cool? So that's what's going on behind the scenes, this algebraic process, right? That's what we're doing. All right, so that's the end of the topic, essentially, not the end of the section yet. So we move on to find another geometric setting, finding the distance between a point and a plane. Okay, so what's the picture? I mean, the formula is there, okay? That's the formula, but let's get the geometric point of view, so we can see where is this formula coming from. I'm not going to derive the formula strictly. I'm just going to give you the idea. How do we get this? How do we, how do we end up with this projection thing that in the end it's just that, right? Okay, so number 1, we want to find the distance between a point and a plane. However, that point which is not on the plane, okay? Let me kind of paint the plane, okay? So, let me plot a point in the middle of nowhere that it's not on the plane, say here, right? So that's the point right here. Let me call that point what? Let me call it Q. All right? It's actually labeled as Q, okay? So, also, again, what else is there on the plane that I forgot to draw here? What's there on the plane?
P.
What is that?
P.
What was that again? Sorry.
P.
P. Oh, okay. Well, we're gonna get another point P. So, but what else that belongs to the plane, so to speak? The direction vector, right? A direction vector. Well, that direction vector can be anywhere. It doesn't matter. It can be here. It can be there. It can be there. Really doesn't matter. Okay. Well, why is that? You'll see. Okay. Let me just get one. I just need one, not too many. Okay. So that's the vector n. We are going to use this vector to find the distance between that point and the plane. That is, we are going to find this projected distance right here that makes a shadow on the plane like this, right? Now, how are we going to find that distance? Projection of what? Okay, because do you guys agree that this distance right here, it's the same as this distance there? But check this out. Did you see this distance right here is not the same distance as the magnitude of that vector n? It's only a portion of it. That is a projection of something. What is that something anyway? Okay, that's something. So we need another vector. We need a vector with finally the point P that goes from this point P that is on the plane to the point Q. Okay? Now, suppose we have the sun in this direction. All right? This sun right here is having this vector in green to cast this shadow or projection onto the normal vector, right? The magnitude of that projection, do you see? Magnitude of the projection, it's going to give us the distance. It's exactly the same as the distance between the point in the middle, that it's not on the plane, and the plane. Yes?
It's like that Mileto theorem?
I believe so. I believe
Yeah,
so.
it's like when you have like a point, you have another point, so and you have to know like the height.
Yes.
You compare the shadow.
Exactly. So that's why I'm having the sun essentially at dusk, right? Or at dawn. I mean, for perfectly horizontal. That's what I mean. And so this shadow is exactly the same as this shadow. So the projection of the green vector onto the normal vector, that's the same as the distance between the plane and the point right here. All right? And well, so essentially the magnitude of that projection, that's the scalar projection, and which involves the dot product between this vector we should get in green and the normal vector. Now, usually the problem is a little tricky because what we're going to get is just an equation of a plane and the point Q. How are we going to get the other point on that lies on the plane? That's the question. We're not going to be given that, right? Otherwise, I mean, it's too easy, right? Well, so here's the thing, okay. A plane contains infinitely many points, agree? For instance, okay, let's have a look at this easy plane, okay? Easy because of the coefficients, 1, 1, negative 1. So if we were to find a point that lies on the plane, then in words, we would need to look for 3 integers such that the sum of the first two minus the third one equals to 1. That's not too hard to do, right? Maybe 1 plus 1 minus 1, that equals 1. So we have our point, right? Okay, but what if you're given this madness here? 3x plus 17y minus 37z equals 93. That plane, all right? And the same point, all right? So to speak, the same point. How are you going to find a point on that plane? Okay, think about this. Can you find 3 integers such that 3 times the first one plus 17 times the second one minus 37 times the third one equals 93? Good luck with that. Good luck with that. All right? How are we going to do this anyway? What's the easiest way to get a point that lives on the plane? Any ideas? Yes, an intercept. Peekaboo the plane. Your favorite peekaboo. In this case, so peekaboo for the easiest variable. Well, in this case, the 3 variables are easy, right? So, and let me write a note right here. Okay. P is any point. Well, yes, any point. I mean, if you can get the algebraic crazy problem, well, that's fine. Congrats. However, go easy. P any point, just use any intercept. An intercept is more than enough. That's a point on the plane. You don't have to get too complicated and find 3 integers, such a blah, blah. No, you don't need that. Okay? All right. So actually, let me make I don't have a GeoGebra for this one. I'm just going to do it by hand. I think it's easy to see this one by hand. Okay. So let me draw a plane again. Okay, so we have this plane with a normal vector, call it n, all right? That contains a point P. We're given another point Q that it's not on the plane, for which we're going to find its distance right here, right? Okay, but we need to define the vector PQ. How do we get that vector PQ? Again, any point on the plane. Remember when I plotted many normal vectors? Because this direction vector can be here as well or can be there as well, right? Remember, vectors are free quantities. It doesn't matter where you have your initial point. It's going to go in the same direction. It's going to have the same magnitude. So technically, there's infinitely many vectors directing this plane. But we're just going to choose one. All right, that's more than enough. Okay. So again, any intercept. All right. So any intercept. You're at the x-intercept, the y-intercept, the z-intercept, it doesn't matter. So because they're all easy variables, right? Now, if you had this equation, 3x plus y minus 4z equals to 12, which intercept would you choose for this calculation?
Y.
The y-intercept. Let me change this to a 9. All right. Okay. The y-intercept would still work well. I mean, if you want to use the z-intercept, that means that should give you the order pair 0, 0, negative 9 over 4. That's still going to work, but do you feel like working with fractions? That's why you would go with the easiest. However, if there's no way around, like this, there will be no way around. You will have to work with fractions in some situations, all right? Okay, so finding the x-intercept. I'm going to use the x-intercept. Okay, let me get rid of this. So x-intercept, that means make y equals to z equals to 0. Okay, and that's going to be simply, okay, so x plus 0 minus 0 equals 1, x equals to 1. All right, so that will be the order pair 0, 1, 0, 0. All right, so we have all the information we need already. So we have the point P, 1, 0, 0, and the point Q, which is the given point, 2, 1, negative 3. We may already create that vector containing those 2 points, because on the formula right here, we need the dot product between vector PQ and the normal vector, actually the absolute value of it, and divide by the magnitude of the normal vector. So PQ equals to terminal minus initial for the 3 of them, 2 minus 1, that equals to 1. 1 minus 0 equals to 0. 1 equals 1. Negative 3 minus 0, that's negative 3. Okay? And then let's find the dot product between PQ and the normal vector. That is, what's that? Okay, PQ, which we just found 1, 1, negative 3, dotted with n. Where do we get the components of n, by the way? Where do we get the vector n? From the plane. What part of the plane? Let's be more specific about it. The coefficients of the plane, the invisible 1, and negative 1, right? So 1, 1, negative 1. Dot product it. And that's 1 plus 1 plus 3, that equals to 5. All right? What else do we need? We need the magnitude of the normal vector. Okay, so the magnitude of n, that equals the square root of 1 squared plus 1 squared plus negative 1 squared. Oh shoot, we're almost done, right? Okay. Yeah, we're almost done. It's about time. So that's the square root of 3. I think I got too excited or something. I don't know. Okay, so the distance. So let's just put everything together. So that's the absolute value of the dot product between PQ and n, and the magnitude of n. That is 5 over the square root of 3. Right? And that's it for today. Let me stop the recording.